Life is like riding a bicycle. To keep your balance, you must keep moving. Albert Einstein said that. And today we're going to keep moving along the regression line. We'll move through some general applications of using the regression line to get predictions. We'll think about confounding a little bit and look at some exercises to help us use the regression line to make functional predictions and think about the contexts where those predictions are valid. Let's first take a brief review of the slope and intercept. Now, we've been talking about the slope and intercept all along, and we keep using the same general model for a line, of a line equation, in which you use the slope and the intercept as substitution values in plotting the line. And sorry, plug issue here. Okay, and when we are finding a slope and intercept, we've looked at a few different methods for finding these points or values. And when you're using correlation and regression, it's a very helpful method to use the correlation coefficient, or R, and the standard deviation of X and Y. As you can see in the figure, and we've been discussing this in previous chapters too, that the slope and intercept can be quantified by the correlation of, can be quantified by the idea that as you go up one standard deviation in X, you move up or down, depending on whether you have a positive or negative association. You move up or down by R times the standard deviation of Y. You can get the direction of the slope from R. If you have a negative association, your R will be negative, and a positive one is going to give you a positive R, so that's going to give you your overall direction. And so we've been exploring this idea, and now we'll just look at some more applications of it. Okay. Here's a great example of finding the slope and intercept of the regression line in the context of a specific problem. You can see here on the x-axis, the predictor, we've got average education, 12.5 years. And this is the average education for males in one of our population samples. And we're looking at how that is associated with income being the outcome variable. This is a common predictor outcome setup to look at too, education as a predictor of income. And so you can see that we can quantify the slope by taking our R value. So if we use, there we go. If we use this equation to give us a general overview, this is our equation for the slope. We could find the slope for this model here by taking our R value, which is, oh golly, conveniently not listed there, but let me verify. So we've got here, a correlation of 0.025. They really buried that one, sorry. So as we go up on the regression line, we can just use this basic model of the standard deviation of x right here is going to be is going to result in an r times the standard deviation of y increase in slope. We're going to actually map out this example on the next problem in just a moment. Our regression line equation is following the exact same model for line equations as we first explored in chapter 7. The basic equation for a line being y equals m, where m is the slope, times x. I'm sorry, it won't I can't erase on this view. Let's see. The slope times the value of x plus the intercept. And we also discussed that there's that the slope could be represented by an m or could be represented by a, still leading to a second general regression line equation that is the same as this one, but uses slightly different letters for each point, where you've got y equals bx plus a, and you can switch these terms around. It doesn't matter whether you write this out y equals a plus bx or, a plus mx. And why are we looking at these different versions? Because the book actually switches from using the mx plus a version, or whichever, to using the bx plus a version when we get into the latter part of the chapter. So I just wanted to remind you that we do have these, they're still using the same model. And we can use the regression line equation to find all the regression predictions by substituting in values in these places here. The values that being for the intercept, the y-intercept, and the value of x. So we can predict specific values of y based on particular, or estimated values of y based on particular values of x. Now, it's important to remember that when you find a prediction line, you can use it to make predictions for participants who are in your study or similar participants from the same population, but you cannot use it to predict the results of interventions, or because a causal study is needed to predict to get data that would be valid for use in predicting the results of interventions. And you also can't extrapolate beyond the sample population. You can only apply it within the specific context in which the data was collected. And this is especially true in an observational study. We also are introduced to this idea of the method of least squares. And the method of least squares tells us that this is basically just another way of, it's in one sense another term for the regression line. So the method of least squares is the method that makes the smallest root mean square error when predicting y from x. And then the least squares estimates are the same as the regression line estimates, because we're using the least squares method of regression. Why have this extra label? Because we're learning about a specific type of regression, but there are actually a variety of other types of regression that we just don't have the space to do in this class. But just a brief example, there's a type of something called logistic regression, which you use when you have a predictor that is a nominal variable rather than an interval level variable. So when we have a different variable type, as you know, that has a cascade effect on the measures that we can use in terms of the appropriate measures of central tendency, the appropriate measures of variability, and it also applies in this context. So that's why we are introduced to the least squares method. Also, a lot of the language out there, the terminology about least squares method, also called ordinary regression, it uses these terms interchangeably. Some people like least squares, other people like to say ordinary regression. The point is that these are all the same thing, and the least squares will minimize the error as measured by the root mean square error, remember, or minimizes your residuals. And finally, we take a look at whether the regression equation itself makes sense. So when you're thinking, does this make sense? The first thing to ask yourself is a basic question about the, based on looking at the data generally, in the context of some of the pertinent factors we've discussed. For example, if there's a nonlinear association between the variables, which you can see from looking at the scatter plot, then the regression line may be quite misleading, and you can't use the regression line to make your predictions. You would use, again, a different set of techniques to deal with nonlinear association. Now, if you have looked at a scatter plot and you've ascertained that you do have a linear association, so you know that regression may be valid for this example, then you ask yourself a second question: does the regression itself make sense? And in this sense, the question is related to, does it make sense conceptually to regress the variable y on x? Is that do this pair of predictors and pair of predictor and outcome variables actually make sense to use in this context? Some things that could affect the use of regression are the presence of some confounding variables. So if you got confounding variables, or in other words, maybe another relevant predictor that needs to be included, then you need to adopt a multiple regression approach, which we looked at a little bit earlier in our lectures on regression. But let's take another look at the general format for a regression, a multiple regression equation. And so multiple regression is quite simply just like normal regression, except that instead of having one predictor, you now have multiple predictors. Now, you can't go up infinitely in predictors. Like if you just say, okay, well, wouldn't it be better to just measure every single possible predictor and put that in the equation? Not really, because if you try to put too many predictors in the equation, then you end up suffering from another problem called overfitting the model. It's called overfitting, and you'll sometimes see this in the literature or something that might be discussed in the framing of a results section. And we have ways of measuring if there's been overfitting or not, but again, that's your next stats class. And so we've got our general model for the regression equation here, and you can see it takes the similar format with the addition of a couple of extra terms. We've still got the y-intercept. We still have the slope times x. Where E, education, is representative of X because, remember, educational level was our primary predictor. But they wanted to come up with a more refined model for predicting income from educational level. And so they added in this additional term here where we have C. Well, C is just another, it's just telling us this is the slope for the second predictor variable. And S is just the value for the second predictor. It's a representative of the measure of parental status. And we would treat it just like we treat the this E, the other predictor, or if we had just our basic regression model, writing it out in the same format that they have here. The same way we would treat this X. So you could substitute in values for each of these to predict. And this is why you end up with problems if you have overfit your model, because then you've got so many values to substitute in here to get to the prediction that there's some error inside each of these measures. None of these are perfect associations. There's always some error. And as we add in more and more terms, we compound that error. And we will be revisiting this idea later in the class, in our course, that is. We'll be revisiting the regression model and the regression line. So this is important in that context. Also, of course, our upcoming exam, where you just should be able to understand the basic idea here, not use it to do predictions or anything like that. But another reason it's very important to understand this model and the way that the multiple regression equation is typically laid out is that often in social and health science research, the researchers like to report their model in these exact terms. So they'll report their statistics to you in a regression model format. So this gives you a lot of insight into reading the professional literature. Let's do a brief summary of the regression line, and then we'll look at the review exercises for this chapter and explore some of the topics we just discussed and some applications. So first, we looked at a couple of descriptive statistics for the regression line, namely the slope and intercept, and how we can use the correlation and the standard deviation to find the slope. And it's important to remember that a descriptive statistic is just giving you some description about the sample. It's not, at this stage, we haven't yet learned how to make inferences about the sample and, to know if relationships are significant or if there are differences. But these are things that we'll be learning about in our next big unit. We'll move from descriptive statistics, which we've been doing, to inferential statistics. And we'll apply some of these ideas we've been doing in the context of description within the inferential context where we're drawing conclusions and determining significance and things. We also discussed here the equation of the regression line, and we've been looking at this throughout our discussion of regression, and this is something you definitely should feel comfortable with on our next exam, using the line equation to make regression predictions. The least squares line is just the regression line for y on x when it And we call it the least squares because it makes the smallest RMS error in the prediction. And the root mean square is a squared term. So this is where the association is coming from. And note that the least squares estimates are the slope and intercept. So if you see, that's quite literally what we mean by our least squares estimates. We looked at scatter diagrams also throughout our discussion of various topics in regression, and a pertinent way to contextualize the value of a scatter diagram is to remember that in addition to looking at the scatter diagram for a linear association or a nonlinear association, you can also use the scatter diagram to help you get an idea of the direction of the association. And once you've moved to the point of mapping a regression line, you want to also use your scatter diagram to make sure that these data are appropriate for regression. And the way to really confirm that is to look for homoscedasticity. And this is generally looks like a football shape in the distribution of points, and it means that there's a similar spread across the distribution. And if you have that, you can go ahead and use the standard descriptive statistics in your model. That is the average and standard deviation of the two variables and the correlation. Remember, if you don't have the homoscedasticity, you might have a nonlinear association or uneven spread, and then you can't use the regression line, and you certainly can't use these descriptive statistics to describe it in the same way. You can't use it to do your predictions. It's also important to consider the context of controlled experiments versus the observational study. A controlled experiment, the slope can tell you the average change in y that would be caused by a change in x. So we can use data from a controlled experiment to predict intervention outcomes because the experimental model, when applied in a context where we've got a randomized controlled experiment, can allow us to draw causal connections between our variables. However, in the context of an observational study, you absolutely cannot draw causal conclusions without let's say for our purposes, you just can't. There are some special contexts where extensive statistical analyses may be used with observational data that's representative of a large population and accounts for a lot of issues we haven't really looked at yet, but can be used to make some preliminary causal conclusions because it would be impossible to measure the outcome of interest in an experimental context. It's just sometimes unethical or impossible to randomly assign people to specific behaviors and things, or experiences, for example. For our purposes, observational studies cannot be used to draw causal conclusions. Finally, just remember that nonlinear relationships can't use the regression line accurately. Your results will be misleading. And this chapter gives us a nice overall summary and brings together a lot of the subjects in the previous couple chapters on regression. And I think we'll find it useful to look at the review exercises next.